Good evening, everyone. In the last class, we discussed about the combination of the cells. We have discussed about the series combination of the cells as well, right? But today, in this class, we'll be discussing about the parallel combination of the cells. Here we are placing a number of cells parallel to each other, right? So this is how the arrangement of the parallel combination of cells is done, right? So let's try to find out how we can calculate the equivalent EMF supplied by the n number of cells which are connected parallel to each other, and each of the cell is having an internal resistance, that's R1, R2, and R3, right, and so on. So what we'll be doing is that we'll be just starting with the this circuit given in the diagram, right? You can see here. So we have a circuit diagram here in this screen, on the screen here. So that you can see that we have three cells, right, put in parallel to each other. That's E1, E2, E3. Each of the internal resistance R1, R2, R3. So what we have done is that we have just distributed the current, right? You can see that the current here is distributed in this circuit. Let's suppose I current is entering this circuit, right, at this point, right? This is the I current, right? And now this I current will be distributed along three branches of this circuit, that's I1, I2, and I3, right? So along this branch of the circuit, the I1 current is flowing. Along this branch, it's the I2 current, and along the third branch, the current flowing is I2, right? It has to be I3, right? That's I3, right? So along third branch, the current flowing is actually I3, right? Such that we can see that the total current has to be equal to I should be equal to I1 plus I2 plus I3, right? I should be equal to I1 plus I2 plus I3, right? So in this circuit, these are the three cells, right? And the equivalent of this circuit is this, right? This is the equivalent of the circuit. It means that we have just replaced all these EMFs of the batteries, right, with the equivalent EMF, and the equivalent resistance, the total resistance of this circuit has been replaced by R equivalent, and this R is the resistance of the external load connected to this circuit, right? So the equivalent resistance in a parallel combination of cells is given by, so equivalent EMF will be nothing. That's E equivalent. That will be equal to E1 upon R1, right? R1 is the internal resistance of a battery of EMF E1, right? Plus E2 upon R2 plus E3 upon R3, right? E3 upon R3 divided by 1 upon R1 plus 1 upon R2 plus 1 upon R3, right? So this will be the equivalent EMF offered by this circuit, right? Where we have three cells, each of EMF, E1, E2, E3, right? And each of internal resistance of the batteries R1, R2, R3. So this will be the equivalent EMF of this circuit, right? Or we can say that R equivalent resistance. R equivalent for the whole circuit will be nothing. It will be equal to this small R equivalent, right? Right? Plus R, right? Plus R. And this R equivalent is nothing. That has to be equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So this will be the equivalent resistance of the internal resistance of the batteries, right? And this is nothing. This is the equivalent EMF of these parallel combination of three batteries or three cells, right? So our total equivalent resistance of this circuit has to be then equal to 1 over R1 plus 1 over R2, right? So just a minute. This R equivalent will be equal to here. It will be actually 1 over R equivalent, right? it has to be 1 over R equivalent. So it will be 1 over R equivalent. That will be equal to 1 over R1 plus 1 over R2, right? Plus 1 over R3. And from here, we can just calculate this 1 over small R equivalent, right? And then put the value of that R equivalent in this equation to calculate the total equivalent resistance of this circuit, right? This is how we'll calculate the total equivalent resistance of the circuit using the concept of the equivalent resistance of the internal resistances of the batteries, right? So let's suppose we have two cells here, right? We're having two cells here, and both the cells are supporting each other. What do you mean by actually supporting each other, right? It means that they are having the similar polarity. See, this is the negative terminal of this battery, this is the positive terminal of this battery. Here we also have the negative terminal and the positive terminal, right? It means that the two batteries will be supporting each other in this circuit, right? Because they are having the similar or the same polarity in this circuit. Then in this case, the equivalent EMF will be nothing. Equivalent EMF will be nothing. It will be equal to E1 over R1 plus E2 over R2 divided by 1 over R1 plus 1 over R2. So this will be the equivalent EMF supplied by these two batteries to the circuit, right? So we can just rearrange it. So it will be E1 times R2 for the two batteries plus E2 times R1 upon R1 R2, right? And similarly, it will be R1 plus R2 upon R1 multiplied by R2, right? You can see this R1 R2 will get cancelled, right? It means that we'll be left with the equivalent EMF as for two batteries having the same polarity, having the similar polarity. That will be E1 R2 plus E2 R1, right? Upon R1 plus R2 upon R1 plus R2. So this will be the equivalent EMF of the circuit, right? For the two batteries or the two cells here in this circuit. So if we have two cells in the circuit, right? This how we'll calculate the equivalent EMF, right? For the two cells or the two batteries in parallel to each other having the similar polarity, right? And the equivalent resistance for this circuit will be nothing. It will be 1 over R equivalent. That will be equal to 1 over R1 plus 1 over R2, or we can write it as R equivalent will be equal to R1 plus R1 multiplied by R2 over R1 plus R2, right? So this is how we can find the equivalent resistance or the equivalent EMF for the two batteries or the two cells which are supporting each other, which means they are having the similar polarity or the same polarity, right? So what happens when the cells are connected with opposite polarity, right? When the cells do not support each other, right? They oppose each other. That's the two cells in parallel are having opposite polarity, right? You can see here in this circuit. There is even a cell of EMF E1 and the cell of EMF E2. One is of polarity plus and minus like this, and another is having this polarity, right? They're having two different polarities, opposite polarities, we can say. In this case, what will be the equivalent EMF, right? So E equivalent will be nothing. It will be E1 upon R1, right? Minus E2 over R2, right? E2 over R2, right? Because they are opposite to each other, they are opposing each other upon 1 over R1 plus 1 over R2, right? So it will be E1 R2 minus E2 R1, right? Over R1 plus R2. So this is how the equivalent EMF will be for this circuit, where the two cells are actually with opposite polarity, or they're opposing each other, right, in a circuit. So this is how the equivalent EMF will be for the two cells which are having the opposite polarity, right? And the equivalent resistance will be same; it will not change, right? It will be 1 over R equivalent. That will be equal to 1 over R1 plus 1 over R2, or this R equivalent will be nothing. It will be same. That's R1 multiplied by R2 over R1 plus R2, right? So this will be the equivalent resistance or the equivalent EMF for the two cells, right? Which are having the opposite polarity or which are having the same polarity, or we can say they support each other, right? In the previous slide, we discussed about the equivalent EMF of the three batteries, right? Three batteries having the Same polarity, right? So let's discuss this question here. The question says that we have to calculate the reading of ammeter. You can see in this circuit, we have two batteries, right? Two batteries which are placed parallel to each other. Each of the batteries having a polarity, each of the batteries having the same polarity. You can see they are having the same polarity, right? That's minus plus here and minus and plus here, right? They are having the similar, or they have been arranged in the same fashion or with the same polarity, right? Correct. And each of the battery is having an EMF of 2 volt, right? And the internal resistance is given as 2 ohm, and here also internal resistance is given as 2 ohm, right? So, but what we have to do is that we have to just calculate the current flowing through this ammeter. That will be the reading observed by this ammeter, right? So what we can do in this circuit is that we can just rewrite this circuit in this fashion. Let's try to rewrite this circuit in this fashion. This is the battery, right? This is the battery. This is the 2 ohm. We can just write this battery first and then try to write this branch, right? So we can just rewrite this circuit in this fashion also, right? And then there will be the third branch, right? With an ammeter in the branch, right? So this is having a 2 ohm resistance. This is the 2 volt battery, and this is also the 2 volt battery. This is 2 ohm resistance, and this is 2 ohm resistance. So they are equivalent to each other. So the circuit has not changed. What we have done for our convenience, we have just written down, we have just uh, drawn the middle branch of this circuit in the bottom, right? So that we can easily try to find out the current or the reading of the ammeter, right? So you can see here in this case, you can see there's two cells, right? These two cells are parallel to each other, and they are having equivalent resistances. Internal resistances is 2 ohm each, right? We can just write their equivalent EMF. So their equivalent EMF will be nothing, right? It will be E1 upon R1, right? Plus E2 upon R2, right? Divided by 1 over R1 plus 1 over R2, right? So it means that we can just replace it with 2 upon 2 plus 2 upon 2, right? 1 upon 2 plus 1 upon 2, right? So it will be nothing. It will be 1 plus 1, that will be equal to 2, right? That will be equal to 2, and half plus half is 1. It means that the equivalent EMF of this battery is once again going to be equal to 2 volts, right? It is going to be 2 volts. And let's try to find the equivalent resistance of these two batteries, right? So 1 over R equivalent will be equal to, that will be nothing, that will be 1 over 2 plus 1 over 2, that will be equal to 1. Or we can say our R equivalent is nothing, it's equal to 1 ohm, right? It's equal to 1 ohm. If this is the 1 ohm, it means that we can just replace this whole circuit with like this. We have this battery of equivalent EMF and the equivalent resistance, right? And then finally we have this resistance of 2 ohm, which is connected with the ammeter, right? Ammeter A, right? Ammeter A. So it means that this is the equivalent resistance of 1 ohm. This is the 2 ohm resistor here. This is the ammeter, and we got the equivalent EMF as 2 volts. So we can just replace it with 2 volt battery here, right? Now you can see that this 2 ohm and this 1 ohm resistor is in series to each other. So this will give us the R equivalent as 2 plus 1, that's equal to 3 ohms, right? That's equal to 3 ohms, right? If this is the equivalent resistance of this circuit now, then the current flowing through this circuit, then the current I flowing through this circuit will be the same current I flowing through this ammeter. It means that this will be the same current read by this ammeter, or we can say I will be the reading of this ammeter, right? So this I will be equal to the total EMF, that's the 2 volts, upon the total resistance, that's the 3 ohm. So 2 or 3 amperes will be the final current that will be read by this ammeter, right? So it means that 2 over 3 amperes, 2 upon 3 amperes will be the current read by this ammeter, right? So this will be the final answer for this circuit, right? 2 over 3 amperes. Let's move on to the next question here. The question here is, if VB minus VA is equal to 4 volt, right? Then X will be. Okay, where to find VB minus VA is given as Okay, VB minus VA is given as 4 volt, right? And we have to find the value of X, right? It means that we have two batteries here, right? You can see that we have two batteries, each of the same polarity, right? Each of the same polarity, correct? And each of these batteries are having the internal resistances of 10 ohm, and this battery of 2 volt is having an internal resistance of X ohm, right? And it's given that the VB minus VA is given as equal to 4 volts. What does it mean? VB minus VA is given as 4 volts. It means that the equivalent EMF for this circuit is actually 4 volts, right? The equivalent EMF for the circuit is actually 4 volts. So we have to just calculate the value of X, right? We know for two batteries or the two cells which are parallel to each other having some equivalent resistances R1 and R2, then their equivalent EMF, we just calculated it, is nothing. It will be, they are having the same polarity. It will be E1 R2, right, plus E2 R1 upon R1 plus R2, right? R1 plus R2. So our E1 here is 5 and R2 here is X. So we'll write it here as 5X plus E2 here is 2 and R1 is 10. So we'll write it as 2 multiplied by 10 over R1 plus R2, that is 10 plus X, right? 10 plus X. That is 10 plus X. And that has to be equal to 4 volts, right? We can just place it with 4 volt here, right? So it will be 5X plus 20 over 10 plus X, right? We can rearrange it in this fashion, right? It will be 40 plus 4X. That has to be equal to 5X, right? 5X plus 20, right? So from here, our 40 minus 20, 40 minus 20 will be equal to 5X minus 4X, right? 5X minus 4X, that will be equal to X, right? It means that the value of X is nothing. It's equal to 20 ohms, right? So the 20 ohm will be the value of X for this circuit, for which the equivalent EMF is nothing. That's equal to 4 volts, right? So the value of X here is equal to 20 ohms, right? So 20 ohm will be the value of X for this circuit. So let's discuss very another important problem, right? Another important problem in your syllabus. That important problem is what we call as Wheatstone bridge, right? It's a very important problem, right? And I will try to understand this, what actually this Wheatstone bridge is, right? You can see here in this circuit, we have this sort of arrangement, right? This sort of arrangement here is in this circuit, right? Let's suppose we're having a battery which is supplying a potential difference of the voltage, maximum voltage supplied by this battery is V, right? We have four resistances. So you can see here, this Wheatstone bridge is actually a quadrilateral type of a system, right? It's a quadrilateral type of a system, right? Where uh, the two opposite ends, or we can say across two ends of the quadrilateral or across one of the diagonals of the quadrilateral, we have connected a battery of potential difference V of our voltage V, and across another diagonal of this quadrilateral, we have connected a resistor that's denoted by here by R5, right? So what actually this is with stone bridge? It's a quadrilateral type of system, right? It's a quadrilateral type of system, and we know that in quadrilateral we have two diagonals, right? We have two diagonals left. And what happens is that across one of the diagonals we connect the battery to the system, right? And across another diagonal, right? Another across second diagonal, we connect the resistor, right? We connect some load or resistor through it, or we connect the galvanometer, right? We connect the galvanometer, right? So it means that Wheatstone bridge is nothing. You can see here in this case, we have the one diagonal here AB, and across AB we have connected a battery, right? Then across another, let me call this a CD, another across another diagonal we have connected a resistor, and such type of system, what we call as such type of quadrilateral system, what we call as Wheatstone bridge, right? This is what we call as Wheatstone bridge. It's a very important bridge, very important circuit, right? Uh, Very important circuit, right? What's the importance of this circuit is that sometimes this circuit, if we have three known resistors and one unknown resistor, right? If we have three known resistors, right? And one unknown resistance with us, right? Then with the help of this Wheatstone bridge, we can actually find the resistance of an unknown resistor. So Wheatstone bridge actually is utilized or helps us. Its application is to find the resistance of an unknown resistor, right? With the help of Wheatstone bridge, we can actually find the resistance of a unknown resistor, right? Now Wheatstone bridge actually can be of two types, right? It can be of two types. One we call as unbalanced Wheatstone bridge, right? Unbalanced Wheatstone bridge, we can write it as WSB, right? And another type we call as balanced Wheatstone bridge, right? There are two types of Wheatstone bridge. One type is the unbalanced Wheatstone bridge, another is the balanced Wheatstone bridge, right? Let's try to see what actually these two types of Wheatstone bridges are, right? So for unbalanced Wheatstone bridge, what happens is that there is no across this diagonal resistor, diagonal resistor, there is always some current flowing through the resistor, right? If some current is flowing through the resistor across this diagonal resistor, then we say that this Wheatstone bridge is the is unbalanced Wheatstone bridge. It's not a balanced Wheatstone bridge, it's an unbalanced Wheatstone bridge, right? And similarly, we can say that in this case, unbalanced is nothing. I is non-zero. I is non-zero through R5, right? Through R5. And in case of balanced Wheatstone bridge, what happens is that actually there occurs a condition at which this Wheatstone bridge, in this Wheatstone bridge, the current through R5 resistor becomes zero. In that case, in that case, we call this Wheatstone bridge as balanced, right? I is equal to 0 through R5, right? Through R5. So this condition we call as balancing condition, right? Balancing condition, and such Wheatstone bridge which is balanced, we call that as balanced Wheatstone bridge, right? Balanced Wheatstone bridge. So balancing condition of a Wheatstone bridge is nothing if through the diagonal resistor the current flowing is zero, and that condition we call as balancing condition, and that Wheatstone bridge will be now called as balanced Wheatstone bridge. So what we can do is that we have to just find the balancing condition for this Wheatstone bridge. We'll try to find the balancing condition for this Wheatstone bridge and try to explore what should be the condition for this Wheatstone bridge so that it becomes a balanced Wheatstone bridge, right? It becomes a balanced Wheatstone bridge, right? So let's try to find it out. So let's suppose there is some current I supplied by this battery, and this current is flowing like this. Some of the current is actually distributed along this branch, that's I1, and some current will be distributed along this branch. Let's suppose that current is I2, right? And this current is I1. The current flowing through R1 and R2 is I1, and the current flowing through R3 and R4 is I2. And there is actually no current flowing through this R5, right? We have to find the condition for which the current flowing through this R5 is equal to 0. And that condition we call as balancing condition of a Wheatstone bridge, right? So let's suppose I1 is the current here and I2 is the current through the lower branch, and I1 is the current through the upper branch, right? So this is the battery B, right? What we can do is that let's assume that the potential at this point is zero, right? If the potential at this point is zero, it means that the whole potential or the whole voltage supplied by this battery will be at this point, that will be equal to V, right? That will be equal to V. That will be equal to V. So potential at this point will be V, and the potential at this point A will also be equal to V, and the potential at point B will be equal to 0, right? So we have just assumed, we can just do by reference, we have taken that the potential at this negative end of this terminal of this battery, right? That's equal to 0, right? And the whole potential difference now will be across the positive terminal of this battery, right? That's the reason the potential at A will be equal to V, right? So now what we can do is that let's suppose at point C the potential is Vx, and at point D the potential is Vy, right? Vy. So the potential at C is Vx and the potential at D is Vy. And for the current to be zero, through this R5, right? If I is equal to 0 through R5, it's only possible in the balance condition, and in that condition then the potential difference across C and T should be equal to 0, right? It means that Vx minus Vy should be equal to 0. Then only in that condition no current is going to flow through this resistor R5, or we can say that Vx will be equal to Vy, right? Vx will be equal to Vy, right? In that condition Vx has to be equal to Vy, right? And I1 current is flowing here. We can just write down this I1 current, right? uh, so the I1 current will be nothing. It will be equal to, we can write VA minus Vx, right? VA minus Vx here. VA minus Vx, right? That will be equal to VA minus Vx, that will be equal to I1 R1, right? I1 R1. I1 R1, right? VA minus Vx will be equal to I1 R1, right? And let's VA minus Vx will be I1 R1, and VA minus Vy, right? VA minus Vy will be equal to I2 R3, right? I2 R3, right? I2 R3. So we know that Vx is nothing. Vx is equal to Vy, right? Vx is equal to Vy. It means that if Vx is equal to Vy, from this condition, we can see that I1 R1 has to be equal to I2 R3, right? I2 R3. I2 R3. Let's call this equation as equation first, right? Equation first. Let's move to the second condition here, right? Second condition. We can see here that the current through R2 is once again I1, and we can write Vx minus 0. Vx minus 0, that has to be equal to I1 R2, I1 R2, right? And similarly, Vy minus 0 will be equal to Vy minus 0 will be equal to I2 R4, right? I2 R4 using the Ohm's law, right? So once again, we know that Vx is nothing. Vx is equal to Vy, right? If Vx is equal to Vy, it means that I1 R2 has to be equal to I2 R4, right? I2 R4. Let me call this equation as second, right? I'm just calling this equation as equation second. And now you look at the two equations, right? You can look at the two equations, equation first and the equation second, right? So we can just divide equation first and second, right? We divide equation first and second. What's we're going to get? That's I1 R1 upon I1 R2, right? That has to be equal to I2 R3, I2 R3 upon I2 R4, right? I2 R4. Now this I2 and I1 will get cancelled. So from here we get a condition. That's R1 over R2 has to be equal to R3 over R4. So this is the condition. This is the condition at which the current flowing through this R5 will be equal to 0, or we can call this condition as the balancing condition, right? So this is nothing. This is the balancing condition, right? This is nothing. This is the balancing condition. The balancing condition is that the ratio of R1 and R2 should be equal to R3 over R4, right? R1 over R2 should be equal to R1 over R2 should be equal to R3 over R4, right? Or we can say product of the diagonal resistors, that's R1 multiplied by R4 should be equal to R2 multiplied by R3. This condition is what we call as the balancing condition of a Wheatstone bridge. And at this condition, the current flowing through the Wheatstone bridge, through the R5 resistor of the Wheatstone bridge is actually equal to 0, right? So the current I flowing through this R5 will be equal to 0, or we can say this galvanometer at balancing condition, at balancing condition, right? At balancing point, galvanometer will show zero deflection, right? Will show zero deflection. It means that the deflection shown by the galvanometer at this point will be equal to zero, right? So this is how the balancing condition is actually done, right? This is the balancing condition, and we earlier said that we use this Wheatstone bridge to find the unknown resistance if the three resistors are known. So you can see in this balancing condition, if we know R1, if we know R2, right? R2, and if we know R3 as well, then we can easily calculate this value R4 using this balancing condition. What we will do is that we will just put all the four resistors in this circuit and try to achieve the balancing condition for this circuit. And once the balancing condition is achieved, the current measured through this galvanometer is zero. We can just apply this balancing equation to find out the resistance of a unknown resistor, right? Let's try to solve some of the questions related to this Wheatstone bridge, right? You can see in this diagram we have a balanced Wheatstone bridge shown, right? If we the question is that a balanced Wheatstone bridge is shown if we interchange the position of battery and galvanometer, then find the current in galvanometer, right? So let's try to see whether this galvanometer is a balanced galvanometer. Sorry, this bridge is balanced or unbalanced, right? Whether this bridge is balanced or unbalanced. So to find out whether this bridge is balanced or unbalanced, what we can do is that we can just try to see the balancing condition for this bridge, right? For this Wheatstone bridge. So the balancing condition, we know that the ratios should be actually equal, right? Which ratios should be actually equal? That's let me call this as R1, let me call this R2, and this as R3, and this as R4, right? So balancing condition is nothing. R1 over R2 has to be equal to R3 over R4, right? R3 over R4, right? Our R1 is 4 and R2 is nothing. R2 is 6, right? That's our R1, R2, right? R1 over R2. And similarly, our R3 or R3 or R4 is 2 over 3, right? So we can just see that this is nothing. This is 2 over 3, or uh, R1, R2 is actually equal to R3 over R4. So it means that this bridge is actually balanced. This bridge is actually balanced. This bridge is actually balanced. If this is a balanced bridge, then the current measured by this galvanometer will be nothing. It will be equal to zero because there will be no current flowing through this diagonal resistor, right? So current flowing through this galvanometer will be actually equal to zero, right? So it's a balanced bridge, right? But the question is that if we interchange the position of battery and galvanometer, right? Let's try to change the position of battery and galvanometer, right? So this is our resistor, right? Let's try to redraw this and then interchange the position between the battery and the galvanometer, right? So this is our 4 ohm, right? This is 6 ohm, and this is 2 ohm, right? This is 3 ohm, right? 3 ohm. Now what we have done is that we have just changed the position of the battery in the galvanometer. Means we will just connect the galvanometer at across these two ends, right? Like this. And battery will be connected across the cross diagonal, right? Across the second diagonal. Now this is the second diagonal. We'll just connect the battery here like this. So this will be the new circuit, right? This is the new circuit, right? This is the new circuit for this condition, right? Now you can see here where these resistors, let me call these resistors as R1, right? And let me call this as R2, right? Let me call this as R3, let me call this as R4, right? So if we still calculate the value of the resistances here, right? The value of the resistances here, this is actually R4, right? This is R3, this is R4, right? So if we calculate R1 over R2, that has to be equal to 3 or 2, right? And if we once again calculate R3 or R4, this is the 6 ohm resistor, right? R3 or R4, that will once again come out to be 6 over 4, that will be 3 over 2, right? 3 over 2. It means that once again R1 or R2 comes out to be equal to R3 or R4 for this circuit, right? For this circuit, R1 or R2 comes out to be equal to R3 or R4, or we can say that this is nothing. This is again balanced. This is again balanced, right? So it means that the balancing condition does not change here in the circuit. The circuit once again is a balanced Wheatstone bridge when we interchange between the galvanometer and the battery, right? And we interchange between the galvanometer and the battery, right? So let's move on to the next question here, right? Let's move on to the next question here. Find current in sorry, it's 2 ohm resistor, right? It's a 2 ohm resistance, right? This is the 2 ohm resistance, right? This is the 2 ohm resistance. We have to find the current through it, right? We have to find the current through this 2 ohm resistance. So current will only flow, right? I will be equal to non-zero, right? In this condition, if it is unbalanced. If it is unbalanced. If it is unbalanced, then the current through this 2 ohm resistor will be non-zero, right? Otherwise, current through this 2 ohm resistor will be zero when it's a balanced one, right? When the Wheatstone bridge is balanced, right? How can you identify whether it's a Wheatstone bridge or not? The identification is that across it's a quadrilateral type of system, right? Across the two ends of the battery, right? Across the one of the diagonals of the quadrilateral, we connect the battery, and across the second end of the diagonal, we connect the resistor, right? You can see that across both the ends, A and B, right? Across the same end, A and B, both the resistor, right, as well as battery is connected. If both the resistor as well as battery is connected, so it means that it's not a Wheatstone bridge, right? Not a Wheatstone bridge. So it's not actually a Wheatstone bridge, because in Wheatstone bridge we connect battery across one diagonal and the resistor across another diagonal. But here you can see that battery as well as resistor is connected along the same diagonal. So we cannot say it as a Wheatstone bridge. It's not a Wheatstone bridge, right? But the property of the Wheatstone bridge is that the battery and the resistor has to be connected across two different diagonals, right? So let's try to find out the current flowing through this 2 ohm resistor, right? So whatever the potential difference will be, right? Whatever the potential difference will be across, whatever the potential difference will be across uh, the battery, that's 10 volts, right? The same potential difference will be across these two ends, that AB, that will be VAB will be once again equal to 10 volts, right? If potential difference across the two ends of this 2 ohm resistor is 10 volts, it means the potential difference is non-zero, and it has got some resistance. So definitely there will be a current according to Ohm's law, that will be I is equal to VAB over R, right? VAB over R. So this current will be nothing. This will be equal to 10 volts upon 2 ohm, that will be equal to 5 amperes, right? It means the current across this 2 ohm resistor will be nothing. It will be a 5 amperes current, right? And this is not a Wheatstone bridge actually, right? It's not actually a Wheatstone bridge, right? Because in a Wheatstone bridge, what we do is that we just connect the battery and resistor across two different diagonals, right? But you can see here in this circuit, it appears to be a Wheatstone bridge, but actually it's not, because the battery as well as the resistor are actually connected along the same diagonal. So that was a catch in this question, right? So let's move on to the next question here, right? So you can see here we have a sort of triangular shaped circuit here, right? So it's a triangular shaped circuit here, where each of the resistors are having the resistance equal to R, right? And we're asked to find the RAB, or the equivalent resistance between the 2 points A and B. So whenever we are asked to find the equivalent resistance across any 2 points, so across those 2 points, we're supposed to connect the circuit with the battery across those 2 points only, right? So it means that if we just pick this end of this circuit, right? This end of the circuit and place it here, right? Place if we just pick this point A and place it here, then the circuit will be rearranged equivalently in this fashion, right? It will be like this. It will be like this. So this will be the rearrangement or the new arrangement of this circuit, right? These two circuits are actually equivalent to each other. What we have done is just we have just flipped the point A, right, across the left hand so that the shape of this circuit changes. But you can see now in this circuit, it looks like a Wheatstone bridge, right? It looks like a Wheatstone bridge. Why it's a Wheatstone bridge? You can see that this is the point A and this is the point B. And whenever we have to find the resistance across given 2 points, it means that we will try to connect the battery across those two ends, right? So we'll just connect a battery across these two ends, A and B, right? So let V be the battery or V be the potential difference of this battery, right? So across next diagonal, right? C and D, where the resistor. It means that it's clearly a Wheatstone bridge. Now we'll try to see whether it's a balanced Wheatstone bridge or unbalanced Wheatstone bridge, right? Since we can see that all each of the resistor is of resistance R, and R, and it's a very symmetric circuit, right? It means that it has to be a balanced Wheatstone bridge. So what we can do it R1 over R2 will be equal to R3 over R4, right? It means that R1 over R2 has to be equal to 1 and R3 over R4 is also equal to 1. So this is the balancing condition, right? If this is the balancing condition, right, then the current flowing through this resistor will be equal to 0. If the current flowing through this resistor is equal to 0, it means that this resistor is actually of no importance in this circuit. It means that we can just clearly remove this part of this resistor right here from this circuit. If we just remove this resistor from this circuit, it will be left as, we'll try to remove this, right? We have just removed the resistor, right? We're left with this situation only, right? So you can see now we have four resistors left, R, and R. So R and R here are two resistors in series, right? So it will have equivalent resistance of 2R, right? And these two resistance are also in series. We have equivalent resistance as 2R, right? Now they are connected to the battery V, right? Now these two resistors, 2R and 2R, are parallel to each other. So their equivalent resistance will be equal to R, right? So it means that final equivalent resistance across AB will be nothing. It will be R, right? So we can say that R equivalent is nothing. It's equal to R, right? So it means that we can actually find the equivalent resistance of a circuit also using the balancing condition of a Wheatstone bridge, right? So let's move on to the next topic, right? The topic is that electrical energy and power, right? Electrical energy and power. And we know that whenever in a circuit the current flows, right, there is always the heating effects of the current, right? Because continuously when current is flowing or the charge is moving, right, there is always loss in energy, right? Because of the drifting of the electrons and collision of these electrons with the other atoms in a conductor, right? Due to that, what happens is that after each and every collision of an electron with the atom, right, the energy is lost, right? Or we can say there is always a transfer of energy, right? There is always a transfer of energy and loss of energy, right? And that energy in the circuits or the resistors or the conductors appears in the form of heat. So that energy, what we call as heat energy, right? And this energy is of very utmost important for us, right? We use this energy in our electrical heaters in our daily lives as well, right? So that thermal effect or the heating effect actually comes out from the loss of energy by the electrons, right? In the circuit or in the conductor, right? So how do we actually calculate this loss in energy, right? Or the heat generated in a circuit when current flows through the circuit, right? So what we'll do is that let's suppose that we have a resistor we have a resistor of resistance R, right? And we have connected a battery of potential difference or the voltage V, right, across this resistor, right? So what happens is that when the current flows through the circuit, there is always some charge flowing through the circuit, right? And the potential difference, or we can say that there is always a work done by the battery, right? There's a work done by the battery, right? So because the battery supplies the charge, right? Battery supplies the charge. If the battery supplies the charge, it means there is definitely some work done by this battery, right? So let's suppose dq charge, there must be some current flowing through this circuit. Let's suppose dq charge is supplied by the battery, right? Dq charge is supplied by this battery, a potential difference V. So we can say that the work done by this battery will be nothing. It will be V dq, right? V dq will be the work done by this battery, right? V dq will be the work done by this battery. And let's suppose I is the current flowing through this circuit, then this I will be nothing. It will be the dq over dt, right? This is the current flowing through this circuit, right? So we can just replace dq with this I dt, right? I dt. This will be the current, right? So our work done will be nothing, right? It will be dq, we can replace it with I v dt, right? Right? I v dt. So we can replace this, we know V is equal to IR, right? V is equal to IR, or we can replace this V by I, we can replace this V by I into R, right? So our the dW work done will be nothing. It will be equal to I square R dt, right? And whatever the work done by work is done by this battery, right? And this whole of the work done is actually converted into the heat energy, right? Because this resistor actually does not retain any energy, right? Unlike in capacitor or the inductors, right? So we cannot store energies in resistors, right? Whatever current is flowing through the resistor, whatever the energy is supplied by this battery, right? So this whole energy is actually lost because this resistor actually cannot actually retain the energy, right? And like in capacitors or inductors, right? In capacitors, what happens is that we continuously charge a capacitor with the help of a battery, and capacitor gets charged, and there is electric field stored between the two plates of the capacitor, and there is no electric field outside the capacitor, right? In that case, what happens is that whole of the energy in a capacitor is stored between the two plates of the capacitor, or we can say that we try to preserve the energy in a capacitor, right, in the form of the electric field existing between the two plates of the capacitor. But in case of resistors, there's no such property of the resistor or the resistances which can retain this energy. So this energy will be actually lost in the form of heat, right? So we'll just integrate it, right? So if we integrate it, we'll get the total heat loss. So the heat loss will be H, right? So it will be I square R integral of dt, right? Integral of dt, right? So assuming that the actually current flowing is a constant, right? If the current flowing is not a constant, then if a current flowing is a function of some time, right, then the heat loss will be different because we have to then substitute the value of current in that situation as well to calculate the total heat loss, right? In that situation, heat loss will be a totally different, right? But let's suppose some constant current is flowing through this circuit up to some time t, right? Then in that case, the heat loss will be like nothing. It will be I square R integral of dt, that will be t. So the heat loss will be nothing. It will be I square R t, right? So this will be the heat loss, right? This will be the heat loss, or we can say this will be the total work done also, right? This will be the total work done also, and this will be the heat loss, right? The heat loss here in this circuit is nothing. It's I square RT, right? So the heat generated in this circuit is I square RT, right? So it means that greater the time for which the current flows through the circuit, the more will be the heat loss, right? Now let's define the term what we call as power, right? Power. Power is nothing. It's the rate at which the work is done by this battery, right? That will be defined as the rate at which the work is done. That's dW over dt, right? dW over dt, right? And we know that our dW is nothing. We just calculate this dW small amount of work that's equal to I square R dt, right? I square R dt, right? I square R dt for a constant current, right? If the current is not constant, then we'll be using this differential equation, that's dW over dt. We'll just take the derivative of this, right? Let's suppose that the current flowing through this circuit is a constant current, that will take I as constant, R is also constant. Then the power delivered, then the power P delivered to the circuit will be nothing. It will be equal to I square R dt over dt, right, over dt, or we are left with nothing. That's equal to I square r, right? I square r, right? This is the constant power supplied. It means this is the power supplied when the current flowing through the circuit is a constant, right? And resistance is also constant. Resistance will only be a constant if there are actually no temperature change, right? So this is the ideal situation we're talking about. But practically speaking, whenever there is a current flowing through the circuit, right, there is always a heat loss. If there is a heat loss, there is always the change in temperature in the resistor, right, or the resistances. Whenever there is a change in temperature of a resistance, then definitely the resistance of a resistor actually changes, right? So this equation is actually ideal equation, right, to calculate the power. But practically, this is not so, because whenever heat is generated, right, heat is developed in a circuit, the temperature of the circuit changes. When the temperature of a circuit changes, then the resistance does not remain same. It actually changes, right? So this is the P equal to I square R that will be calculated the power, or we can just rewrite it as V square over R, and also we can write it as V multiplied by I, right? So these are the three forms of the equations of this power we use generally, and all two equations V square over R and I square R has a slight significance in the combination of the circuits, right? Whenever we talk about the power consumption in series circuits and the power consumption in parallel circuits, then we'll try to see what is the significance of these two equations, right, in those circuits, right? So till then, I think we have to stop here, right? We'll discuss all those series combination and parallel combination in case of power consumption in the next lecture, right? So let's stop here. Till then, take care and goodbye.